Okay. All right, welcome everybody. Thank you for joining. It's 6 o'clock, so I guess we can start with introductions now. Since I'm already talking to you, Vincent, why don't you go ahead and start us off here?
Sure. My name is Vincent. I don't write too much Rust at the moment, but I think it's one of the more interesting communities. I see a lot of like activity and people are doing interesting things. So yeah, I'm just that's why I'm here tonight. That's it for me.
All right, sounds good. Oh, got a lot of people joining here. Just give me a second to admit them.
It's a crazy number. I don't know if you want to do intros. I mean, even if they're 1 minute each, it might
I'm
be
not.
more than an hour.
I know, I know. I don't tend to do intros for the entire time. I usually only go for like, I don't know, 5 to 10 minutes, and then we cut off. So we're not going to go through every single person. Um, yeah. So just to let you all know, Alexei from Bitco on our side here is helping me with the recording. So he will be recording this talk, and yeah, it'll hopefully be uploaded onto YouTube later. We do have a Rust Meetup Vancouver YouTube channel that basically doesn't really get used very much at all. It's just kind of an archive for videos and stuff. But yeah, that's that hopefully we'll have something to upload today. All right, wow, that's a lot of people. Okay, I'll do my introduction next. So hello, I'm Jonathan Louie. I'm the organizer of the Vancouver Rust Meetups, and I've been working at Bitcoin Technologies for the last 4 years as a software developer. I personally don't write any Rust on the job, but I do know a team that does write Rust, and I do, I guess, consulting for them. So yeah, that's pretty much me. Um, we'll go to Bo-chun since he's one of our co-organizers.
Yeah, I'm here. Hi,
Yeah, you're
Jonathan.
here.
Hi. Yes, hi everyone. I'm the co-organizer of this Vancouver meetup. I work for a gaming company called Skills. So I have just started the first Rust project in our company, trying to figure out how to write a plugin for Envoy proxy. So also played Rust for about 2 years. So it's not a lot of the production experience. So very glad to meet you here today.
Awesome. Okay. We'll go to Anna since she's our speaker.
Sure. Can you hear me? Is the sound alright? I'm not sure
Yep,
if
we
I
can.
selected. Okay,
We can hear you.
great. Yeah, so I'm Anna. I work at Mozilla. I'll be presenting later today. So yeah, I mostly use Rust in like personal projects and a little bit during like at work we also use it.
Cool. I'm gonna go to Dean since he just joined. You want to give an introduction, Dean?
Yeah, so it's been a while since I've joined, moved and everything. So thought I'd join up. I can't stay. Got to go to the kids' soccer game, but thought I'd make an appearance and see what
Cool.
y'all are doing.
Yeah, long time no see. Good to have you.
Yeah.
We'll go for another minute here. Let's see. Peter, did you want to go next? Peter Kale?
I'm a Rust hobbyist. I love the zero cost abstractions and the control, and that we can make we can squeeze every microsecond and every we can use the memory to the best. Off to you, Jonathan.
All right. Sounds good. I think we should just get started with the talk now. So Anna, if you want to present your screen, then we can get started.
Sure. It's saying I can't present. Let's see. Try again.
Are you on a Mac? Maybe it's your security preferences or something.
Maybe. Yeah, I'm on a Mac.
All right, I think we have to give Anna a minute here to rejoin.
Sorry about that, but yeah, I needed to restart my browser.
Yes, we will. So the recording should be posted on YouTube, and we do have a Rust Meetup Vancouver YouTube channel. It only has like one video right now, but yeah, this will hopefully start building up our catalog.
Can you see my screen?
Yep, I can see your screen.
Okay, because I cannot see my screen. But yeah, that should be fine. So you can see how it's like changing slides, just to check.
Yep, that's working.
Okay, awesome. Cool. Yeah, I guess I can get started then. Yeah, so this talk will be about how REST is used in Mozilla's data platform. And maybe first a bit more about me. So yeah, that's me. I'm Anna. I work at Mozilla as a data engineer. And yeah, I've been at Mozilla for about 1.5 years. If you don't know what Mozilla is, we're basically the ones that make the Firefox browser, but we also offer other products like Mozilla VPN, Pocket, Hubs, and lots of other cool things. Yeah, I'm located in Vancouver. You can find me on most platforms under the username Scholzen. So yeah, I guess it's fair to say that most of our like components in our data platform, they're not implemented in Rust. They're actually like mostly implemented in Python or Java, but there are some components that are implemented in Rust. So I'll be talking a bit more about them. But I guess first of all, like most people might ask themselves, like, why do we collect data in the first place at Mozilla? And I guess it's a fair question. And the answer is we basically have to make sure that the entire web works with our browsers. So we offer like a bunch of different browsers for many different platforms, like Firefox for iOS, Firefox for Android, different desktop platforms. So it would be impossible for just the developers alone to make sure that the whole web works on these products. So instead, we need some data to see how our browsers perform in the wild. So yeah, it's especially important for getting some performance data, but also data about feature usages. And a lot of the data we collect is actually publicly available. So there's, for example, this measurement dashboard where you can find how long the garbage collection usually takes, but there are also like other dashboards available. And yeah, so in general, the data that we send is usually aggregated on the client, then sent to our pipeline, and then aggregated again, and then stored for later analysis. And yeah, so it's really nice for engineers that they don't have to rely on their locally collected data, but they can use the data from like millions, hundreds of millions of browsers that we collect. Yeah, so when we collect this data, we follow 3 principles. First one is to stay lean. So we regularly reevaluate if we actually still have to collect certain data. So if it doesn't make sense to collect some data, we also just disable it. Or sometimes people like think about what data we should collect to make better decisions, for example. The second principle is to build security. So basically to ensure that data is collected in a secure way, that no user information is collected, that only really technical data is collected. And yeah, the third one is to engage users. So whenever we want to collect some new data, there is a public process. You can follow them, like all of these processes can be followed on Bugzilla. So yeah, whenever someone wants to collect some data steward needs to approve that, and then it can be implemented and collected. So yeah, any user can comment on these like proposals, and yeah, if they have concerns or other ideas.
Is there a way to maybe blow up the text there a bit? Because some of the text is a bit small. I don't know if you can make this any larger.
Is that better?
It's better than it was before, so I think that's
Yeah, it's already on like full screen or like.
Mhm. Yeah, I'm not really sure if there's anything you can do about it. But...
Yeah. There's also like I also uploaded the presentation to the GitHub repository, so there's a PDF of the presentation that should make it easier to read if you follow it like locally.
Okay.
Yeah, so I guess I'll be moving on. Yeah, I hope it's readable, at least to a certain degree. So yeah, our data platform. So this is basically a very high level, simplified view of our data platform. And it probably makes sense to walk through how the data flows through that system before going into more detail of how the individual components work. So in general, as I mentioned before, we have a lot of different devices in the wild that run Firefox. So we have Firefox on mobile, Firefox on desktop, and all of these devices, unless it's disabled, they send some telemetry data. And to send the telemetry data, the platform engineers, they use a telemetry library. So there is a telemetry library for mobile, which is implemented in Rust, and it's working on iOS and Android. And there's also a legacy telemetry library, which is currently used in desktop, but will soon be replaced by the same mobile telemetry system. And yeah, using that telemetry library, it's easy to send telemetry data. We also call the messages that are sent to our telemetry servers pings. So once these pings hit our ingestion edge, which is implemented in Python, then they're put through the decoder. And what the decoder basically does, it decompresses the messages, it parses them, validates them, and then later writes them to the database. But for the validation, what the decoder basically does is to validate the messages against some schemas that we have defined. So just to make sure that the messages that are sent, they're in a certain format that we expect them to be in. And yeah, these schemas are written as JSON schema, and they also can be used to derive the table schemas that we use in our database. But our database system expects a different format. So you cannot just deploy the JSON schema format, but you have to convert it into a different one. And for this conversion, we have a tool called the JSON schema transpiler, which is implemented in Rust, and it will, convert these schemas, and then we can deploy them to our database system. We have to deploy schemas regularly if we want to collect new data, and or if we want to make changes of how the data is collected. So once the data flows through our decoder, it's written to the database system, and then analysts or data scientists can use that data that is stored. Okay, so I'll be talking a bit more in detail about the mobile telemetry library that we use and the JSON schema transpiler. So first about the telemetry library. We also call that library Glean. And Glean is the telemetry library that performs the measurements and sends the data from our Firefox products to our telemetry servers. It's, as I mentioned before, just used on mobile right now, but will be used for desktop by the end of this year, next year. So we're currently migrating. And yeah, before we had Glean, each browser was basically implementing its own telemetry system. So there was a separate telemetry system for our Firefox for iOS, Firefox for Android, Firefox for desktop. And they were basically doing all the same thing. But yeah, it required a lot of maintenance to keep them basically on par, that we could ensure that they were sending like the same data. So it made sense to consolidate that all into one library. And that's how Glean was born. And yeah, since cross-platform was a must, we decided to use Rust. Yeah, so one of my colleagues, Jan Erik, who is like working a lot on Glean, he also gave a talk about the details of Glean. I linked it here, so I'm probably not going to go into as much detail as he went into his talk. So if you're interested in more lower-level Glean, then you can check that out. Yeah, I also have to say that I personally do not work on Glean. I only have to work with the data that is sent through Glean, so I might not have all the answers about all the low-level details. But yeah, I'll do my best. Okay, the Glean SDK. So the Glean SDK is split into several layers. We have the Glean Core, which basically builds all the functionality that Glean provides. Then on top of that, we have Glean FFI, which is the lower level binding between, which is the binding between the lower level Rust code and the higher level Kotlin or Swift code. And yeah, Glean Swift is used in Firefox for iOS. Glean Kotlin is used in Firefox for Android. We also have some more implementations, but those are the main ones. So yeah, let's look at the Glean Core. So the Glean Core, basically the main component there is a Glean struct. So this struct holds some state. It has some main logic, including storing some data, uploading data. It also offers an API that can be used. And it also holds a collection of different metrics types that we want to collect. And these metric types, they're also implemented in the Glean Core. And they can be as simple as just counters, as we see here, but there are more complex metric types like timing distributions, histograms. Yeah, there are a lot of different types. But yeah, they basically are all like implemented as a struct. And then some methods for the counter metric here. We have some add method, which will increment some value in the storage. And then later that value might be sent inside a ping. Okay, so that's basically all there is to the Glean Core. Then on top of that, Glean FFI, which is the connection between Kotlin and Swift to the lower level Rust crate. So in general, most languages, they are able to talk to C code, but they cannot talk to Rust code by default. So what the FFI layer does, it translates the Rust code we have to C code, and then it can be used by these other languages like Kotlin or Swift. So FFI, which stands for Foreign Function Interface, allows to define external functions and expose functions without any name mangling, and it also allows to invoke some unsafe code that would otherwise be illegal in Rust. So writing the FFI layer in Rust is actually relatively simple. So it mostly just looks like Rust with some additional attributes. So looking at the Glean initialize function here, which basically sets up Glean, you see it's basically just Rust code. There is this no mangle attribute at the top, which basically signals to the compiler that this function should be just taken as is. So the function name should not change, but just be put into the binary as is, so callers can find it later. Otherwise, if we wouldn't have this attribute there, the function name would be changed to something pretty much random. yeah, next there's this extern C in front of the function name. And it's basically just used to indicate that this function will be exposed and ensures that the C ABI will be used. And the C ABI itself is quite restricted, so it doesn't know certain types. It doesn't know generics or references. And there's always some translation between Rust types and C types required to pass the data around. But yeah, so for example, I'll be probably later talking about a bit more in detail how the string type is different in Rust than in C. But yeah, that's basically all there is. So yeah, what this function does is we pass in some configuration, we make sure that this configuration can be parsed, then we instantiate a new Glean struct and call some setup code, and then Glean is initialized. Okay. Yeah, when working with C, C needs to know what functions actually exist. And how it does that is it has some header files. And these header files contain all the available functions, essentially. And to generate these header files from our C code, from our Rust code, we use cbindgen. So yeah, using cbindgen, the header files are generated. What this would look like for the previous Rust code we have with our Glean initialize, yeah, it would look like this. Basically, we have our Glean initialize function and the FFI configuration object that is passed into the function. Okay. One other library that Glean uses is called FFI support. And FFI support is a library that was started by another team at Mozilla, the application services team. And the application services team also has to write a lot of cross-platform libraries. So what FFI support does, it bundles a lot of patterns that are usually used throughout FFI code bases. So it makes it way easier to write FFI code and makes it look mostly just like Rust. Yeah, so FFI support will do all the type conversions under the hood for us without us having to write any like conversion code. And how it does that is it provides this into FFI trait. So this trait basically generalizes the conversion between Rust and FFI compatible types. And for example, for strings, strings are a bit different in Rust than they are in C. So strings in C, they have to be terminated by a null byte, which is not the case in Rust. So we need to have some special conversion there. There are some libraries like CString, which will do that for us. But having this into FFI trait, we can also use it for other types, which might be slightly incompatible otherwise. So yeah, this into FFI type just makes it way more convenient to write FFI code. Okay, so compile targets. Yeah, in general, as I mentioned before, Glean has to run like on different machines. So we might want to compile Glean on a Mac, but maybe you run it like on Android or Linux. And luckily, the Rust compiler is a cross compiler by default. So it knows how to turn Rust code into some other machine's machine code. And when installing Rust through RustUp, you can get a list of installed targets. So just by typing in RustUp target list, you can list these targets that are installed. The Glean SDK itself is currently compiled for 11 different targets. So like Android, iOS, different desktop targets. And yeah, it's pretty easy to install and add new targets. It's just basically RustUp target add, and then you can compile the Rust code. And yeah, that already mostly gets us there. We can compile the Glean Rust code, but compiling, like using the Rust compiler, it doesn't know anything about the target-specific linkers or library. So for that, we also need the Android SDK and NDK when building for Android, or Xcode when building for iOS, which has all the tools we need. So I'm not going into much detail of how that works, but essentially what we have to do is we have to write some wrapper code in Kotlin or Swift. And these wrapper implementations, they talk to the C API. So they talk to they call the functions that have been generated through Glean FFI, and they provide a nicer API for Swift or Kotlin for engineers to work with. So yeah, that's essentially how it works. There are more Glean implementations. So there's Kotlin, Swift. We also have an implementation for Python, C++, which will be used for Firefox Desktop. There's a JavaScript implementation so that we could also send telemetry data from websites. There's also a nicer Rust implementation with a nicer API to use. But yeah, whenever we have to make some changes in the core, all of these changes need to bubble up that stack, right? So we have to make like some updates in Glean FFI. We have to update all of these wrapper implementations, like the Swift or Kotlin implementation. And yeah, the more implementations we support, the more effort it would be to make all these updates. So coming this year and next year, we will use UniFFI. And what UniFFI is, it's basically a multi-language bindings generator. And the only thing you have to do is write Rust code. So you don't need to write any like Swift or Kotlin specific code. The only thing you need is Rust. And you also have to write some web IDL to define the interface of your cross-platform library. So yeah, in this example, we'll just imagine like a to-do list that we first define using web IDL. So we have our to-do list object. The to-do list has some method, a constructor, some add item, and then it's implemented in Rust. So we have our to-do list struct, it holds some items. All of the methods are implemented in Rust. And we take this definition and implementation and throw it against UniFFI, and then UniFFI will generate the FFI layer for us. It will take care of the type conversions, and it will also generate the Python, Swift, Kotlin code, whatever it supports. So yeah, we don't need to write any wrappers anymore. It makes it very convenient. Yeah, so that's essentially how Glean is used, how Glean works. And yeah, through Glean, we get all of our telemetry data. And yeah, so I guess I'll move on to the next component, which is the JSON schema transpiler. So the JSON schema transpiler, it doesn't have a nice icon like Glean does, but it's nevertheless important. And the JSON schema transpiler is the tool we use for transpiling JSON schemas into schemas for Avro or BigQuery. So since this is not a data engineering meetup, some of you might have never heard of BigQuery, but BigQuery is basically the cloud data warehouse that we use at Mozilla to store all our telemetry data. Yeah, I guess most have heard of like AWS and maybe Athena, which is basically the equivalent that is running on AWS. But BigQuery is running on Google Cloud Platform, which is what we use at Mozilla. So the JSON schemas, they are, as I mentioned before, primarily used for validating incoming data, but they also contain enough information to describe the structure of the data. And so we can use these schemas to define the structure of our tables in BigQuery. All of these schemas, they are open source, so they are in the Mozilla Pipeline schemas repository. So you can basically see exactly the data that we store in our databases. And yeah, let's look at what these JSON schema actually look like. So as the name already indicates, it's basically just JSON. So we can look at the JSON schema of the crash ping. The crash ping is sent when Firefox crashes, and it contains information like the crash date, some optional ID. We also have the stack trace and lots of other information. But yeah, looking at the JSON schema, we can see that it defines certain fields and also the expected shapes that the data that is defined in these fields should be in. So for the crash date here, you can see there's this regex, which defines how the date should look like. And if the data doesn't match that format, then we just reject it. So yeah. So yeah, how does the JSON schema transpiler fit in here? So we have all these JSON schemas, they're in the repository, and we can use them as input for our JSON schema transpiler and then generate the BigQuery schemas and then deploy them to BigQuery. And what the transpiling looks like is, so on the left, you have the JSON schema. It's a simplified version of our crash ping. You have the crash date, some nested fields, and on the right side, we can see the corresponding BigQuery schema. And the BigQuery schema format is, again, it's JSON. It does look different. So we still have these nested fields. We can see that it doesn't have any information about the expected shape of the data, because our database system, BigQuery, doesn't care about what the data actually looks like. It cares about the types. So these still exist. It cares about the names of the fields. If you look closely, the names, they changed a little. So in the JSON schema, they're in camel casing, but our database system expects snake casing. And we also added some information like the mode, which tells the database system that fields can be null. Yeah. So for the transpiling, we make heavy use of the SerDJSON library. So it's a very handy Rust library when working with JSON. And it was also one of the main reasons why we decided to implement the JSON schema transpiler in Rust in the first place. So yeah, it provides efficient and safe ways to convert JSON into its Rust representation. So schemas are deserialized directly from JSON into Rust structs and enums using SerDJSON. And yeah, let's look at how that works. So enums are heavily used throughout the entire code base of the JSON schema transpiler. And enums, they're pretty similar to algebraic data types in functional programming languages, and they also support robust pattern matching. And a very common pattern that we use in JSON schema transpiler is to abstract schemas into tags and types. So types, they basically form a set of symbols and rules for producing a sequence of these symbols. So you can look at the code here. We have this type enum, which can either be an atom. Atoms are basically just types like booleans, integers, strings, or it can be a list of these atoms. And using types, we could parse our schema if we only cared about the types. But in general, like our schemas, they have different fields with different names. We might also want to add some descriptions. So we want to have some additional attributes associated to these types. And that's where tags come in. So tags are basically attribute data associated with a type. And yeah, looking at what this looks like, we still have our type enum, we still have our atoms, which are some basic types, but now we have also record. And yeah, record is basically just a hash map that maps fields to other tags, which allows us to express these nested schemas that we have. And yeah, tags, our tag is just a struct, which has some name, some data type, some description. We could add some more attributes if we would care about that. But yeah, tag essentially represents a field in our schema. So we could, using the tags and types we have, we could express that in Rust and basically like write some Rust code that could be serialized to a schema, which we basically see here. But I mean, normally it's not something we want to do, right? The JSON schema transpiler usually just wants to take an input, transpile it, and then produce some output. So we never really write Rust code to describe a schema. So for actually making sure that we can transpile from one format into another, what the JSON schema transpiler does is it has a separate module for every format that we support. And in each of these modules, we have specific implementations for these types and tags. So right now we support BigQuery. So we have a BigQuery module and BigQuery specific types and tags. We have JSON schema. We also have Avro. And the JSON schema transpiler does not support converting directly from, say, JSON schema to BigQuery. But instead, we first convert into some internal abstract representation, which is called AST here. And the main advantage of that is that if we want to add more formats, then, for example, let's say we want to add a new proto buffer schema, then we don't have to implement all the logic to transpile to Avro, to JSON schema, to BigQuery, and the other way around. But instead, we only have to implement logic to transpile to the AST representation. So it does simplify a lot of things. And so for translating from one type into another, we have this translate from trait. And the tags, like here we can see the BigQuery specific tag, which implements this translate from trait. It offers this translate from function, which takes as an input an AST tag and some context, which has some configuration stored. And essentially, we just map data types from one type into another. And then at the end, we can return the BigQuery specific tag, which represents our BigQuery schema. So yeah, basically, just to reiterate what this whole process for converting JSON schema into BigQuery looks in code is we have this convert BigQuery function, takes some JSON input, and we have this into AST function, which basically parses the input and uses 30JSON to create the JSON schema tag from the schema, and then we translate this JSON schema tag into an AST tag, which is returned and then translated into a BigQuery tag. And this BigQuery tag can then be serialized into JSON and probably written into some file, which we then can use to deploy the schema. So yeah, that's basically what the JSON schema transpiler does and how it works. So yeah, there are some other components that we have that are implemented in Rust, but they're either pretty similar to the Glean telemetry library and how they work, or they're just like minor unimportant components that are not really worth talking about. So yeah, that's basically all there is. So yeah, if there are any questions about like data at Mozilla, about Rust, about life, I'm happy to answer them.
That
I have a
BigQuery.
question. How is the ingestion edge implemented?
It's implemented in Python. So we used to have it implemented in Java and Dataflow, but it wasn't very performant and pretty expensive. So it's basically some Python logic running on Kubernetes.
I see we have a question in the chat. Is a similar process to the JSON transpiler used to migrate data inside of BigQuery?
Like, okay, it's probably hard to ask other questions, but what do you mean by like migrating in BigQuery?
Sorry. So if you have schema migrations happening in BigQuery itself, like, do you read and write it back, or do you just leave the data as is?
Yeah. So we usually don't read the schema of our tables, write it back, and then write it again. So basically, the source of truth is inside this repository, and these schemas reflect exactly what is currently. Well, yeah, if they're already deployed, then well, they essentially should reflect what is currently deployed. Like as soon as there is a change made to the repository, it gets deployed automatically. So they should be on par. There might be some like delay, but I guess it doesn't really matter.
So I had another ingestion edge question. So you mentioned it was Python and running in Kubernetes containers. So are those running in GCP's Kubernetes since you're using BigQuery?
Yeah. So yeah, it's running on GKE, Google Kubernetes engine.
And you found that to be more economical than running it in Dataflow?
Yeah. It's way cheaper.
Oh, okay. Thank you.
So the decoder itself is still implemented in Java, and it uses Dataflow. Yeah, it just didn't make sense to re-implement it because I mean it's a lot of effort and also time costs money. But yeah, for the ingestion edge, it made a huge difference.
Do you use some kind of queuing system like a Kafka or a PubSub?
We use PubSub as queuing system.
Oh, got it. So that would be sort of between these SDKs and the ingestion edge?
Yeah, exactly.
Got it. Okay. Thank you.
Do you reuse any paths with protobuf to JSON? I believe that's protobuf used between the Firefox processes.
Yeah, it's possible. So we don't use protobuf in our like data platform. It might be used inside the browser, but I'm not sure about that.
Thanks.
All right. Do we have any other questions?
So, what does the decoder do, as distinct from the ingestion edge?
Right. I mean, so the ingestion edge is just to receive all these messages and pings, and then it doesn't do very much. In some cases, the ingestion edge also republishes some data, so there are also some other like PubSub pipelines that we have for other systems. But yeah, it basically just gives these messages that it receives to the decoder. It does some batching, so it's not all like real time and streaming. So yeah, it doesn't do very much, I guess.
Got it. And the decoder?
So yeah, the decoder takes these messages. These messages are usually like compressed, so it decompresses them so that it can read them and validate them against the schemas. It also enriches them with some information that we need. It also, in some cases, we want to scrub some messages that we're not interested in or that might contain sensitive information. So all of that is done inside the decoder.
Got it. And that does decoder does use GCP's data flow.
Yeah.
Got it.
All right. Do we have any other questions or?
But when you said that the decoder can strip some potentially sensitive, did I hear, or private data, does it mean that this is an extra precaution to filter out if if by any case the client or something goes wrong and there's something leaking out?
Yeah, so all of our code, like for all of our browsers, is public, right? So there are some organizations or people that just simply clone like Firefox for Android and basically rebrand it, rename it, but they forget to turn off like their telemetry. So we still get telemetry data sent from some other browser clones, possibly, which we don't really want, right? Because we don't know what kind of data they're sending to us. So that's where we strip and scrub these messages.
All right. Cool. Do we have any other last-minute questions, or? All right. Well, I think that's it then. Thank you very much, Anna, for the talk. That was a very excellent presentation. Oh, actually, I have one final question. What did you use to present this? Because I see you have some kind of a web app running.
Yeah, I think it's called Reveal.js. So I wanted to write like, hold on, I didn't want to use LaTeX for it, but just write it in like HTML, CSS. So yeah, that's what I used.
Okay, cool. All right, well, thank you very much for the talk. Next, I think we'll move on to our news segment. So let me just share my screen here. Give me a second. All right, everyone can see my screen?
Yes, sir.
All right, awesome. So I didn't pick out a ton of news stories this month. Been kind of busy. Didn't really look around for too much. But I did spot a few interesting things. So first of all, if you haven't heard, Rocket now has a 0.5 release candidate out. And what's really cool about this is that you can finally use a Rust stable with this. So that's really cool. If you're interested in using the Rocket web framework to build a web app, then yeah, you might want to consider looking into this. Next, we also have a new version of ripgrep that was released. This fixes a security vulnerability on Windows. So for Windows users, you may want to upgrade. Otherwise, yeah, there were some bug fixes and performance improvements apparently. So that's all cool stuff. Good to know. And lastly, I had picked out a couple of game development related articles. So yeah, we've got this new backroll RS networking library, which implements rollback netcode. If you aren't aware of how what rollback netcode is, you can check this out. They explain it here. It's been kind of a big thing in the fighting game community if you've been following that, especially if you're familiar with like the Evo tournament for fighting games. There's been quite a kerfuffle about games not using rollback netcode, and so the online is generally very laggy and not very playable, especially for tournament settings. So rollback netcode has been picking up quite a bit of steam lately, and it's kind of cool to see Rust being used to write some rollback netcode libraries now. And here's another one. This one's a little bit more recent. So we've got two competing implementations here, I guess. And so you can check that out if you're interested. But yeah, that's pretty much it. So as usual, I'm going to be posting all the news articles on our event page. And then yeah, I'll be sending that out in the reminder email at the end. Do we have any questions, any discussion, any feedback, anything that anyone wants to talk about, Rust related?
I have one question. I've been learning coding in the last 2 years. I I want to get practical about Rust. So do you have any suggestions on what kind of easier real world things I can do with it?
Real world things you can do with Rust. I mean, I see a lot of people trying to use it as like a general purpose programming language. There's also quite a few people trying to use it in like embedded systems. So, yeah, I mean, you can try and use it for a number of projects. Maybe the ecosystem isn't fully fleshed out in certain niches, but I don't really know. I don't really know how to give you like a great answer for that.
Okay. Other guys, do you have any suggestions for me?
We recently having some practice like choosing a different programming language. We're trying to figure out how to replace our internal services with the like open source solutions. And when we have limited scope, there's only a few choices like Lua code, TypeScript, and Rust. So given the performance requirements, we need to using a very high performance and very precise memory management. So this Rust will be our only choice. That's a roadmap actually how we pick up particular languages. So firstly, we will be limited by the framework we choose. The framework gives us a few choices, but the next one is how we limited by our business requirements.
Okay, thank you.
Yeah, I've also seen Rust used in a lot of like WebAssembly projects. So if you're interested in picking up a WebAssembly project, then Rust has pretty good support for that.
Okay. I just spent some time on Vue.js, and I came to know that there's Dino project going on. It was written in Rust, and I may be able to leverage my knowledge about Rust so I can get a better understanding of Vue.js or just find something, get my hands dirty. Do you have exposure to Vue.js and how do you see some connections between Vue.js and Rust?
Where I work, we use Vue in our front end, and we have our backend is a part of our backend is a API written in Rust. We deal with some data and we send it to the front. It's kind of simple, but it's a use case.
Yeah, I see. Thank you.
Is Vue.js is like the front end framework, right? Just like React.
Yeah.
Okay. So I haven't really used Vue.js. I've done React in the past, and when I saw Vue, I really liked it more. But now that I'm doing Rust, I switched over to Seed.rs. It's a front end framework that compiles to WebAssembly. And it's entirely in Rust. You kind of write your HTML using these macros, and then you have like these callbacks that form a message, and then you have some special code that handles the message, and it works really well. I really like it, and it's entirely in Rust, so I'm able to share a lot of code between the backend and the front end. I recommend checking it out. There's also YEW. It's another front end framework for in Rust. So you might, depending on your I guess coding style, you might prefer one more than the other. But I really like them, so recommend looking at them.
Yeah,
Thank
I
you.
think I've heard that U is more like it's more like Elm, right? The Elm programming language.
You know, I thought U was more like React, and Seed was more like the Elm model, but maybe it's
Oh,
backwards.
okay.
I'm not sure.
Yeah, maybe I'm mistaken.
Yeah.
That's I'm pretty sure. No, I like like U is named after like a tree, just like Elm, and so I think they were going for something similar there. But yeah, I'm not sure.
Oh, I just so in my mind, like when I see React, I thought of, I see like you pass in these props and you do the same in Vue. So in my
Okay.
mind, I'm just like, oh, they're very similar. And with Seed, there are really no props you're passing in. It's all like in one model for each component that you build out.
Okay, sounds interesting. I never really tried anything other than like React, so. Any other questions, comments, feedback?
I have a comment. When I started learning Rust, I decided to get practice coding, solving problems on LeetCode and Code Wars. And these websites dedicated to mostly algorithmic problems. So it was double shot. I learned Rust and I learned some algorithms. So I can recommend.
Actually, I have a problem with those algorithms. I did spend quite some time on LeetCode, Code Wars, and those I can solve the easy questions, but for the medium and hard questions, the algorithms are over my head, and I think it takes too much time, too long for me to learn. I I want to get my hands on some more practical, more easier things so that I want to find a better learning curve for myself.
Okay, I agree with you.
So one recommendation I have, it's sort of general, but if you find an open source project you like, they usually tag the issues with like beginner or like with help wanted or easy for a first timer. So various projects have been doing this, and it's designed to help people who are not so familiar with the project to start contributing to the open source project. So you might want to try that out.
Great, thank you.
By the way, Bochan, did you want to chat after?
Yeah, sure. Let's have a chat.
Cool. Yeah, any other questions, feedback, comments, anything? Otherwise, we'll just end the meetup here. Going once, going twice. All right. Well, thank you all for coming to today's Rust meetup. Yeah, we'll be posting the news articles again as usual. And yeah, hopefully we'll have another talk next time. So, yeah, thank you very much. Take care.
Thank you, everyone.
Thank
See you
you.
next time.
Thank you.
Bye.